I'm actually talking about a few different topics. So I'm going to go back and forth between this presentation and the other one. So we're going to start talking about graphs and Euler circuits and weighted graphs. And then halfway, I want to talk a little bit about permutations, combinations, and the counting principle. These are the topics that you probably already started seeing or that you will see next week. So it's a little bit crammed. So once again, welcome everybody to the Friday Happy Math Hour. And let's start with the concept of a graph. A graph, I know we think of, usually when I talk about a graph, we probably think of a parabola or a line, but we also study graphs in a different way because they're very useful. In fact, one of the main applications is that graph theory is applied in computer science, and specifically, we use them to understand how computers or an algorithm or software as AI works and self improves. So this is a complete different type of graph. So I'm going to go over the definition, which is a graph has vertices. These are the points. And it also has line segments, which we call edges. Now, they don't need to be straight lines. They could also be curves. For example, in the pictures below, I have a graph that has only 5 points. And then I also have a graph, a second example. It has 4 points or four, I'm going to call them vertices. And we have one, two, three, four edges. So as you notice, some of them are line segments, the other ones are curves. Think about it like connections. So it's an edge that connects two vertices. On this example, I have another graph. And something that this shows different is that you may have an edge, which we call the loop, that starts at the same point and it ends at the same point. And last, this is what we call a complete graph. And this is, I'm assuming, a typical picture, kind of like a pentagon with a star inside. Why we call it a complete graph is because there is no more connections that you could do. So if you have five vertices, these are all of the possible edges. So all of the possible connections or segments have been made. An example where we can use graph theory, often when we have questions like these where we have a table, it is much easier to represent the problem by using a graph. So the question here is to draw the graph that represents this scenario where we have mobile phone companies and they have roaming agreements between between two networks. And so let me put the table. So this is my, each of the vertices, each vertex is going to be one of these companies. There's five. And the table is supposed to display, like when you read the table, if you start, let's say, you could start on the rows or the columns. If you start on the rows, there's no need to have a roaming agreement with itself. Roaming is usually when you're borrowing someone else's network. So like here, none of them need a roaming agreement with itself, but Mobile Plus does not have, because it says no, we talk more. And then Mobile Plus has an agreement, yes, with Supercell, no with Airwave, and yes with Lightning. So to represent this scenario, I'm gonna make edges between those companies where there is an agreement. So for Mobile Plus, I see two of them, so there's two edges connecting Supercell and Lightning. Then if I move on to the next one, which is Talk More, there's only one agreement with Supercell, so you see the edge in there. The next one would be Supercell. To be noted that even though I see three, one, two, three, some of these connections I've already made. So Supercell and Mobile Plus, I already had draw the edge, so I don't need to draw it twice. Talk More and Supercell already had that connection as well. And so the only one that I added was Airwave. I'm sorry, wait, I see I have it in two different names. I'm, I'm I'm just gonna call it airwave as it is on the table. So probably this is the misspelled airwave. And the last airwave has a connection with supercell and it's already there, but it also has a connection with lining. So I need to add one more edge connecting lining and airwave, which there it is. And last, lining has connections with Mobile Plus, Talk More, and I'm sorry, Mobile Plus and Airwave. The Airwave connection have already been made, so I just needed to draw this extra edge, which it's already included. Okay, so now I have all of the possible connections. And by looking at the graph, it's a little bit easier to answer questions. For example, which phone company has roaming agreements with the most carriers? In the graph, this would translate to which vertex has the most connections. So we see Mobile Plus has two edges coming out of it. Lining has two. Airwave has two. Supercell has three connections. So that would be the correct answer, huh? And the second question, which company can run with only one other network? We see there's only one edge going into Talkmore, so the answer is Talkmore. Also, because we can draw these graphs in different ways, it is very useful to understand what are equivalent graphs. So equivalent graph is essentially saying it is the same graph, even though it's drawn in a different way. And you look at examples right below. So the conditions are they need to have the same number of edges and vertices, but also the edges have to form the same connections between vertices. For example, all three are equivalent, and the reason is because I see five vertices on each one of them. And notice that exactly the same connections are made. So, for example, on the further left, you see that B is connected to all of them. And you see that exactly on the other three graphs. So, even though it's three different ways, think about this as the same graph. So we're going to call them equivalent. So the same properties, the same um, conclusions that I can make about one would also apply to the other two. So here I wanted to trick you and give you an example of whether these two graphs are equivalent. And the answer is no. And you could emphasize that if they do seem to have the same vertices and they even have in a from a just one glance at it, just from a broader look at the graph, you might be able to say, well, it is exactly the same graph. But the fact that I changed the name of the vertices implies different connections. So drawing the edges as two letters, for example, DA means that there's an edge between D and A, and DB there's an edge between D and B. Then if you look at the other graph, you see that now the ones that's on the center is BA, it's B. So there's edges BA, BC. But if you analyze the same vertex, the one that represents the same one, so for example, D here has only two, in this graph, the vertex D has two edges connecting to A and connecting to B. On the other graph, now D has connections to E, B, and C. So these would not be equivalent because of that. So the way that you label your edges and not the label, the way that you label your vertices may create different graphs. Not necessarily, but this is an example where it does. Okay, so now the next topic is a path. A path in a graph is basically kind of like you could say like traveling from one vertex to the other one by moving along the edges. So let me give you, well, before I give you the example, we could also have what we call a closed path, and I'm gonna also call it a circuit. A circuit, basically, if it starts on the same place and it ends. So usually when you do a circuit, it's so in some cases, like an electrical circuit, it's closed. So you start at one point and you end at the same point. This is a picture that shows four vertices and then different edges in blue. And an example of a path would be going from A to B to A to C. So going on the bottom and then B, it doesn't matter which one of these edges you take, and then going back to A and then going to C. An example of a circuit would be starting again in the middle, A, now going to B, now going to C, and then D, and then coming back to A, because I started and ended on the same place. Now, what we really want to focus on is what we call the Euler circuits. And I know many people pronounce this Euler. I think it's very common in the US. But Euler was actually a German mathematician. So the correct way would be Euler. You could do it either or, it would be fine. Euler or Euler. So again, I hear it both ways. And what is that? So an Euler circuit is a circuit that uses every edge, but never uses the same edge twice. So basically, you gotta use all of the edges, all of the different connections. You may cross through a vertex more than once, so that's fine. But the edges, they may not be repeated. They may not be used twice. Let's look at an example. So here I have a graph that has a bunch of vertices. It's 8 of them. And then you see a lot of edges. So, by the way, for example, if I start on F, from F to D, this is one edge, and from D to B, that's a different edge. It's not, there is no edge between F and B, because then I would need to have a line that pretty much goes around it, like connects those two immediately. I just thought of that right now, just to kind of like, so that would be from F to B, but the graph did not had anything before. Now, what I want to show you is an example of an Euler circuit. So starting on B, so to have a circuit, I have to start and end at B. And I got to travel all of the edges once. So for example, I could go to D and then to F and then across to H and then to E, up to C, left to A, A to G, and then you could see how I can finish by going to E and then B. So there was no repeated edges. I didn't travel along the same line twice. If I had, you would have seen um, like a double line, huh? You would have seen a thicker, bolder line, meaning that I passed twice through the same edge. So this was an example of an Euler circuit. If I wanted to represent it in letters, and the book does this, it's very common in our book. This is how they represent paths or circuits by giving you the sequence of letters. So it would be starting on B and then D and then F and then G and so on. And notice how it starts and it ends on B. So this creates a circuit. Actually, I passed through B. I started on B and then I passed once and I ended on A. That does not matter. That's why the definition says the path may cross through vertices more than once, but the edges themselves, the lines, were not repeated. So I have another example here. Does the graph shown below have an Euler circuit? And so I'm going to start on B, and then I'm going to go to E, and then I went up to C, follow the arrows, and then to G, and then to D. And from here, I don't have a choice. I gotta take the path that connects D and F. And from here, it seems like I have three choices. But if I want to have a circuit, I would go back to B. However, if I go back to B, this was not Euler because it didn't travel through all of them. It is a circuit, but it is not an Euler circuit, because to be an Euler circuit, I had to use all of the edges. And notice all of those blue ones that doesn't have a red on them, I did not pass through them. I did not use them. So now further analysis will reveal that this graph does not have an Euler circuit. And this is how we analyze it. If we focus at that particular vertex B, it doesn't matter if you want to start on A. I actually started on B, but it doesn't matter where you start. If you want to start on A or on G or on D, whatever you want to start, to have an Euler circuit, I would need to travel all the three different edges. And I started by pointing to the one E from E to B, that one. Let me point it out here. And then I have another one, BF and BG. So these three connect to B. But think about this way. At some point in my path, in my circuit, I would need to go into this vertex because I gotta use all of the edges. And then I would need another one to come out. For example, I could come out through BG and continue my circuit. But then this is where the issue happens. Notice that now, at some point, if I want to travel through all of the edges, I would need to use this one, FG. And the problem is, if I went in and went out, then the only way that I can go back to B, the only way that I can use this edge is by going into B. But the moment that I want to get out of it, I can't because I already used all three, and then I would need to repeat one of them. And so that's not allowed. I would need to use more than once one of these edges. So these already is telling me that it is impossible to create an Euler circuit in this graph. It doesn't matter where you start. I know it may seem like I'm focusing on B, but that's why I draw the arrows in this way. If you start on B, basically it is the same answer. And you saw the example that I gave you before. I started on B and I still was not able to create the whole graph. And in a similar way, um, even if I start on any of the edges, B would be a troublesome vertex because I wouldn't be able to cross all of the edges without repeating one of its edges. And that's basically the idea. A similar situation happens in other edges, not only B, but also C, also E, and also G. And if you start to pay attention, like why cannot use all of the edges of those vertices, you will realize that the good ones would be A, F, and D. And if you separate them, you start looking at what we call the degree of a vertex. And the degree of a vertex is how many edges meet at that vertex, how many edges go into or out of it. For example, if I have this graph and I want to see if there's an Euler circuit, then what I seem to need on each one of these vertices is I need to have an even number of edges going into it or coming out of it. So if I analyze each one of them, for example, vertex A has four edges. You could see them there, 1, 2, 3, 4. So it's degree 4. And then vertex B has degree 4 as well because there's four edges meeting at that vertex. C has 2, but then D has 5. That's where I get an issue. That's what was happening on the other graph. That when I looked at B, it had only 3 edges, and that did not allow me to have an Euler circuit. So this graph, also the answer will be no, because I wouldn't be able to travel through all of the edges connecting D. And of course, D is not the only one. You could also look at E that also has 3. So in order for the existence of an Euler circuit, so if I want to be able to create an Euler circuit, I need all of the vertices of the graph to have even degree. There has to be an even number of edges meeting at each one of the vertices. If there's at least one, or if there's two that do not have that property, then it's impossible to create an Euler circuit. Well, these Euler circuits, they're actually very famous in connection with a city in Germany in the 1700s. Um, the citizens of this city called Königsberg attempted to take a stroll that would lead them across each bridge and return them to the starting point without traversing the same bridge twice. None of them could do it, no matter what they chose to start. And so the picture kind of like shows you the scenario. Now, if you look at a map of this city in the 1700s, there's like houses and everything, and it does not look like this. But this is just a simple representation of the map. So it would be interesting to go and check it out. Look up. This is a city still exists, I believe, in Germany, Königsberg, which, by the way, they pronounce it Königsberg. Uh, and so it turned out there was really nobody knows why they wanted to do this. Almost this 1700s, probably there was no TV, so they were more critical thinking, and they just wanted to see if it was possible. There was no other purpose, maybe curiosity. They just wanted to see if they could go around the city and use each bridge only once. Not right now, after what we just talked about, you will recognize this as an Euler circuit. They were attempting to create an Euler circuit. And the way to create a graph, and this is one of the important things, because we look at this and you're like, how do I create the graph? Well, a natural way would be that the masses of land, these would be my vertices, and basically the bridges are my edges. And so let me highlight it again. So all of these side, all of it, all of this that is in green is represented just by that one dot. So if you want to get to that side of the city, you can go from these to here, or from here to here. These are the only ways connecting from this middle land, from this little island into that side of the city. And so this would be like my edges on the graph. And then so if I make all of the connections between vertices, between the points, this is how the graph looks like. So this is the graph that represents the city, including the bridges. They were trying to see if they could start at one point and then cross all of the edges of this graph. So if I kind of like go and count, this graph has one, two, three, and four vertices, and it has one, two, three, four, five, six, seven edges. So actually, you already saw this graph. I wonder if you remember, I had a picture of this one at the very beginning. And well, the answer, we already know the answer. The answer is, um, and that's probably became a famous question because they did not have always in mathematics. I think back in the day before we had like Google and AI, just because you didn't know the answer to a question, that doesn't mean that that question is not possible to be answered. Now it's so easy for anyone just to go online and find a bunch of information and then you may find the answer right away. But so that was their thinking, like, well, just because I have not been able to find a circuit that goes through all of the bridges doesn't mean that doesn't exist. And so they wanted a proof, they wanted somebody to convince them. Or if you cannot convince me that it's impossible, then show me one, like find one. Just because you haven't found it doesn't mean that it doesn't exist. But now we have, I just explained the tools. Huh? The answer to this is impossible. They couldn't do it because it's literally impossible. It doesn't matter how you try it or where you start, because you have actually not just one. I only focus on this one. this vertex has odd degree, has one, two, three. And so you wouldn't be able to go in, go out, and then there will always be an edge that you cannot cover without repeating twice one of the others. But it's actually not the only one, huh? Also over here, I have three edges meeting at that vertex, and I have three over here. So the only good one is actually the middle one. Actually, that one also is impossible. One, two, three, four, five. So the whole graph was just impossible. All of the edges have odd degrees. So technically, it's not possible at all. All right. So this was just kind of like a curious connection. Now, later on, they started calling also an Euler path in a similar way, like go through every edge once, but do not repeat edges. So now you don't need to start and end on the same place, but you do need to go through all of them. And the modification, which is called Euler path theorem, is that, by the way, Euler it was a mathematician, a very famous mathematician who did a lot of incredible things. He was the one that solved the problem of the Königsberg um, question. And so the modification on what if it was a circuit, all of them had to have even degree. Well, if you wanted to path, then you needed only two vertices with odd degree. So this would be kind of like your starting point and your ending point, and the rest of the vertices need to have an even degree. And so this could be applied in this graph. I'm going to skip the whole scenario, but I think it's somebody that is on a bike, on a mountain bike, going around a national park, and this person wants to go around the trails exactly once. Basically, this person is trying to create a Euler path. And so you analyze all of the vertices and you realize that A has degree 3 and F has degree 3 and all of the other ones have even degrees. They're even numbers. So that means it is possible, but you have to start at A or at F. And so I created one of these things. You could see how this biker would travel through all of the edges and then started on A and ended on F. And then I put here the path. Okay, very quickly, I want to mention weighted graphs because I'm getting to the middle of the hour and I want to transition into the last part, which is combinations and permutations. Um, Now, the opposite type of graph is what we call a Hamiltonian graph. So now we're switching it around where we want to visit each of the vertices, each of the vertex once without visiting any vertex twice, regardless of whether all of the edges are used or not. So I do not need to cross through all of the edges, but I want to make sure that I pass through each vertex without repeating vertices. So it's kind of like the flip side, huh? Before I wanted all of the edges without repeating edges. Now I want all of the vertices without repeating vertices. The modification is that I don't even care if I don't cover all of the routes. So maybe think about this like a delivery. You want to go into all of the stores, um, or you want to deliver into all of the different places, and you don't need to go through all of the streets. Huh? You just want to make sure that you can find a path that covers all of them. So if it starts and it ends at the same point, we're going to call it a circuit. And a graph that contains a Hamiltonian circuit will be called a Hamiltonian graph. Hamilton was, again, an excellent mathematician and more of a physicist, I believe. He created a lot of theories that help, with the whole development of like modern physics. This is very, very famous in physics. And this theorem, I believe, answers that question. It says, consider a connected graph. So you need to have a graph where all of the vertices have at least a connection, so you can reach through all of the vertices with at least three vertices and no multiple edges. Let n be the number of vertices in the graph. If the vertex has degree of at least n divided by 2, then the graph must be Hamiltonian. And then note a multiple edge would be this example. These are multiple edges between A and B, so we don't want those ones. Now I'm going to skip this example because I'm trying to get to um, the weighted graphs, which is the last part. And actually, this is very important in computer science. You know how I mentioned at the beginning that graph theory is used to model AI. So AI is usually trying to improve what is the fastest way, what is the most accurate information. And weighted graphs is actually typical. And the way that it's done is that you have values on, so each edge has a weight, has a value. An example to kind of a more practical example rather than AI. To talk about AI, I would have to complete different talk. But then this is a simple example where you can see the weights. So a tourist in San Francisco wants to visit 5 locations by bus and then return to their hotel near Moscone Center. The table shows the nearer Moscone Center travel times between locations. And then NA means that no bus route is available, not a direct bus route. Find two possible routes and compare their total travel times. So this person wants to San Francisco, visit all locations, and then return to the hotel near. So wants to, I believe, start and end at the same place, which is the Moscow Center, which must be probably close to the hotel of this person. That's what we would want. Huh? And notice that you have the travel time. So from this place, from the center, Moscow Center, to go to the Civic Center, that is 18 minutes. To go to Union Square, that would be 6 minutes, and so on. Well, this is the graph. And the idea is, for example, this person could start on Moscow Center and then go to the Civic Center and so on, right? I actually created different ways. So this would be one path, going to the Moscow Center, to the Civic Center, to the Union, um, then all the way down to Fisherman's Wharf, and then to the Coit Tower, and then to Embarcadero Plaza, and then up to Moscone Center again. But then notice that the total time was actually 1:14. And a better way of doing this, because that's what the person wants to do, huh? It wants to find, like, probably wants to take the shortest route. The shortest route would be this other way would be actually shorter, because if you go in this direction, you go through all of the places, but you actually save 1 minute. Not a lot, huh? So that's just what a weighted graph is. Usually it has weights, it has a specific values on the edges that are part of the question. Okay, so this was just a very quick and brief review of graph theory. And the last part of the hour today, I want to talk about a little bit about uh, counting principle, combinations, and permutations. Obviously, graph theory is very nice because there's a lot of visuals. But this one, even though there's not as many visuals, there is, but not as many, is usually faster for students. It's very intuitive, so I think also you're gonna like it. Um, a typical example would be if you flip a coin, what are the possibilities? And usually we represent them with heads and tails. So with one H for the heads and T for tails. So flipping a coin has two possibilities. We call that the outcomes. This one, I need to actually click here. How many outcomes are there if a regular six-sided die is rolled? So what are the possibilities when you roll a die? And then die is the singular of dice, by the way. So dice is actually the plural. I know many times we say like, hey, pass me the dice, but technically you should say, pass me the die. And so if you have a die, or I'm just gonna say them either or, dice or die. If it's one, then that would be six possibilities, which they can be listed inside these brackets. So we call that the sample space. The sample space has all of the possible outcomes, all of the possibilities. Notice, very important, they got to be separated by comma. This is what tells me that it's six. If I don't put the commas, then it is represented as a single thing, like a single large number. And also, those braces are very important. This goes back to set. At the beginning of the course, we talked about sets. And so the sample space is a set, is the set of all the possible outcomes. It says list and then count the number of different outcomes that are possible when one letter from the word Tennessee is chosen. So in this question, actually, the tricky thing would be that letters that are repeated would be exactly the same one. So, what are the different possible letters that you can obtain? Well, you have the T, you have the E, the N, and the S. So, there are only four possible outcomes. We're going to call an experiment any of these activities like flipping a coin, tossing a dice, drawing a card from a deck of cards, or so anytime that we use like we perform an experiment, we mean that we do one of these activities. The set of all outcomes is called the sample space. I mentioned that. And it has to be written between those two brackets. Usually they're called braces. Some people call them curly brackets. So they need to be inside that. And the different outcomes, they need to be separated by commas. Remember, in a set, the order is not important, so you could change the order. That does not affect it. We also called an event when you have one or more possible outcomes. So if this is your sample space, an event would be like just one of them, say three, or maybe you can have two of them, like two and five. I always try to relate this. Think about that you're gambling and you win if it lands on two and five. So the event of winning would be like those two possibilities. The next, am I going backwards? I think I'm going backwards. All right, I'm going to skip this part. So I have this example. It said two-digit numbers are formed from the digits 1, 3, and 8. Find the sample space and determine the number of elements in the sample space. So I always like to tell my students, like, give me an example of this. Like, what would be one possibility that follows the instructions? Well, one possibility would be 38 because this is actually thinking of numbers of two digits using those digits. So that would be one. Another one would be, let's say, 81. So the question is, how many do you have? What is the sample space would have all of them, and I would want to know how many are inside. How many? What is the total number of two digits that you can make? And interestingly, on purpose, I well, not necessarily on purpose, happily, accident, I actually did not listed something that repeats, like 33, for example, would be a possible answer since it uses the digit and it's two digits. It uses one of the digits given. So this would be a table that shows you all of the possibilities, and the answer is nine. Huh? So another way of answering these questions is by creating a tree diagram. A tree diagram usually has a start. So we use a point and that is the start. So it's kind of like a graph, what we were just talking about before. We're going to use a tree diagram to create all of the possible outcomes that happen on this scenario. It says a true false test consists of 10 questions. Draw a tree diagram to show the number of ways to answer the first three questions. And the first three questions. So even though there's 10 questions, we just want to know what are the different ways of answering the first three. And so you could start, the star is like just kind of like to represent what are the possibilities. And so on the question one, you could either answer true or false. And then once you answer that, once you answer question one, you will go and answer question two. But now each one of them has two possibilities because you could start with true and then answer true, or start with true and then answer false, and the opposite, huh? Start with false and then answer the second one in the two different ways. But because it is three questions, then you gotta like go one more, and it's like branches of a tree, huh? It's like you're branching extra outcomes. So it turns out the different paths that you can create from the starting point, passing through three of these circles, is actually create. It's called it's one possibility. So if I go all the way on the top and choose this path, that would be true, true, true. This is one possibility in which I answer the three questions, which is I put true in all three. And then a different path would be, let's say, if I go false and then true and then false. So this I will represent it as false, true, false. So in these type of examples, the order does matter because I'm saying that I answer question one, question two, and question three. If I change that order, let's say true, false, false, that's considered a different outcome because now I choose true on the first one. Well, so the total number of outcomes is actually all of the different paths that you can create. And simply by going around from the start through all of the points, so you go from here till the end, that's one outcome. And then you go here again, and then that's another outcome. So you create how many paths you create, and that's actually a total of eight. So this is another way of finding. Um, This is another way of creating. I'm sorry, every time I click on a button, it takes me to the beginning. All of the different possibilities. All right. So now, how many possible outcomes if two dice are tossed? And to differentiate them, we're going to think one of them being red and the other one being white. Students always ask me, does it matter if I have the same die and I roll it twice, or if I roll two of them at the same time or one at different times? And the answer is no. It's still the same outcome. The same sample space applies. And you could see, so each possibility in this picture, it's basically one of these rectangles where you see one outcome on the red and the outcome on the white. And so if I select another one here, it was four on red and five on white. So the total number of possibilities is 36. You can see all 36 listed here. Well, one of our goals is to find how to count the total without having to draw these diagrams. And so what I like to do is I usually put uh, lines and I ask my students, the line is gonna I'm gonna put on top of it the number of ways in which the first die can land, the red one. Well, there's six. And then the number of ways in which the white one can land, six as well. There's six points on it, six possibilities. And so if you toss of them, if you toss both of them and you want to combine them, get one result on the red and one result on the white, then you actually just multiply them 6 times 6, which is 36. And so that's how we could have found the answer without having to look at all of the different, create each one of the different combinations. So this is what the counting principle says, that if you have an experiment, they're calling it multi-stage, which means you have different stages. And each stage, which I'm going to represent with a line, can be performed in different ways. So Stage one can be represented in n1 times. There's n1 different outcomes. Stage two is represented in n2 different ways, and so on. Then, if you want to create an experiment that has each one of these stages, the total number of ways is by multiplying the possibilities of each one. Huh? This would be nk. So there's a total of k stages. So the counting principle is very simple. It just says that if you're putting together different things, you just multiply the possibilities of each one. I like to rephrase it in terms of task. If you have a different task that you want to perform together, you multiply the possibilities of each task. In how many ways can you do task one, task two, and task three? Let's see an example. It says in a horse racing, betting on a trifecta refers to choosing the exact order on the first three horses across the finish line. If there are eight horses in a race, how many trifectas are possible, assuming there are no ties? So there are eight horses in total, and we have, let me just give them a number: one, two, three, four, five, six, seven, eight. In class, I give them funny names or just names like, um, what would be like Fritos, fries. We could give like the name of the horse, and then I think like what are the different ways in which you can select first place, second place, and third place? Well, for example, that would be well, what about if horse number four came in first, horse number eight came in second, and then horse number two coming in third? So this would be a trifecta. Give me exactly the horses and the order in which they come in. So if I change it, let's say if two came in first, four came in at second, that is considered a different trifecta. So order is important. Well, to answer this question, let's use the counting principle. So we have three horses or stages, and I put or task. The task is to in how many ways can we select the horse that comes in first place, where there's eight possibilities. Now, in how many ways can you select the horse that comes in second place? Since there are no ties, then no repetitions are allowed. So if I chose a horse, then there's seven available for second place. And then for third place, this would be six, and you just multiply 8 times 7 times 6, and this is our answer. So the number of trifectas is 336. This is not a question that we want to do by listing all of the different possibilities, huh? All of the different outcomes. Because it would take us a lot of time to write down those 336, and we might actually get it wrong. So do not attempt it. Another question using the counting principle, it says, from the letters A, B, C, D, and E, how many four-letter groups can be formed if A, a letter can be used more than once, and B, each letter can be used exactly once? Well, to answer A, I want to form groups of letters, four letters, and I have a total of five. One, two, three, four, five. So the number of ways in which I can select the first letter would be actually five, because there's five possibilities. What about the second letter? Well, since I'm allowed to use a letter more than once, then still five, and still five. So I just multiply five four times. For B, if each letter has to be used exactly once, then actually once you use the letter, then the number of possibility reduces. And so my answer would be 5 times 4 times 3 times 2. And I have those multiplications on this slide. The first answer is 625, and the second answer is 120. Less possibilities, huh? If you're not allowed to repeat letters. Okay. So I'm gonna just very quickly talk about combinations. So combinations is the different permutations. I'm gonna start with permutations and then I'll transition to combinations. Permutations is the total number of ways in which you can reorder or you can arrange different things. For example, if I have these squares, color squares, the different way that I can arrangement, I would use exactly that counting principle. So I have four different colors. So I have four for the first one. Since I must use each one of them, there's no repetitions. So then there's three left, two and one. So the answer is four times three times two times one. Well, we call, since these appear so often, we have a special way of labeling, which is called the factorial. So that would be 4 factorial. And what that exclamation sign in mathematics means that you multiply from 4 all the way till 1, going through each consecutive number without skipping numbers. So like 4 times 3 times 2 times 1. And so the definition in general, if you have n factorial, would be n times n minus 1, the 1 less, and then 2 less until you get to 1. For example, 4 factorial would actually be 4, well, I just mentioned it had times 2. And if you do this multiplication, this is 24. Final answer. Okay, so by definition, 0 factorial, since it must start at the number and end in 1, it doesn't include actually 0. So we're just gonna set 0 factorial to be 1. So it's kind of an agreement. Don't overthink it. 0 factorial is just going to be 1. I'm going to skip this part. This is just technical. But the part that I want to get to is the permutation. So a permutation is an arrangement of orders in of objects in a definite order. So basically, the order matters. I want to know the different orders that I can have. So order is important. And this is the formula that we use for permutations. Notice that it has the factorial. An example would be a university tennis team consists of 6 players who are ranked from 1 through 6. If a tennis coach has 10 players from which to choose, how many different ranked tennis teams can the coach select? Well, because the order matters, since we're ranking them, like number 1, number 2, number 3, then the order is important. So that means you want to use permutations. So the answer would be the P represents permutations, and then we have N and K. N is the total number, so there's 10 players. And I want to select 6 of them, so K is 6. And to find out the exact number of orderings, then I would apply my definitions. So notice that 10 factorial is a multiplication from 10 all the way till 1, divided by 10 minus 6 factorial. Subtract first, this would be 4. And notice that when you do these questions, you don't need to do all of the multiplications. You can also always cancel the smaller numbers because the larger numbers contain that multiplication. So 10 factorials contains 4 factorial because you're multiplying from 10 all the way till 1. So you can cancel that part of the multiplication with the one below, and that saves you the trouble of doing the division. Then your answer would only be 10 times 9 times 8 times 7 times 6 times 5. Stop right there, which is, if you think about it, I would have gotten to the same answer if I had used the counting principle. This would have been my 6 stages, and those are the possibilities for choosing each stage. So these formulas come from the counting principle, even though it looks like, wait, what are you dividing? They give you exactly the same result. Okay, and then the last thing, I'm gonna just skip to combinations. The combinations changes the formula a little bit, and it adds actually an extra factorial, which is k. And This time in combinations, the order does not matter. So that's the thing to remember. For example, in this question, I have a committee of five is chosen from five mathematicians and six economists. How many different committees are possible if the committee must include two mathematicians and three economists? So from the total five mathematicians, I want to select two. So let me call them M1, M2, M3, M4, and M5. And the important thing is that once you select the two, it doesn't really matter if it doesn't really matter the order. So it would be exactly the same too. And what I like to tell the students to kind of help them, this is what makes the difference when to use combinations and when to use permutations. So usually if you're selecting a group, like a team group, and they're not gonna each of them are gonna do the same task, all of them are gonna do the same task, then it is combinations. The order does not matter. But if each one of them is gonna be ranked, each one of them has its individual task, then the order matters. So because we're selecting two, but there's no indication what each one of them is gonna do, so I can use combinations from a total of five, select two. And for the economists, it's going to be combinations from a total of six, select three. And then I can use my formulas and multiply. So if I want to have two mathematicians and three economists, I'm putting them together. So this is the total number of ways in which I can select the two mathematicians multiplied by the total number of ways in which I can select the three economists. And just for completion, the answer would be, these are my formulas. The simplification is 10, 10 times 20, which is 200. Okay, well, this was all for today. Have a wonderful Friday, and I'm going to give back the control to our host.
All right, thank you, Mr. Tintos, for your presentation today, and thank you to everyone for attending. We greatly appreciate it. Next week, we are going to have, going down here to the bottom of the page, we've got our Happy Math Hour, Math 1332, um, measures of central tendency, measures of dispersion, measures of relative position. And then for Math 2412, we will have the exam 4 review. Our student success topic will be student parent resource centers and the student parent liaison. So thank you everyone once again for attending. Hope you have a lovely weekend and we will see you next week.
Have a nice weekend, everyone. Thank you.